Hello guys, welcome to my YouTube channel Vishwaguru, a problem solver. Today's session we are going to discuss about the center of gravity by moment method. Okay, that is how to calculate the center of gravity or center of gravity formula. Okay, that is how to derive the center of gravity formula by using the moment method. Here we consider an elementary area as shown in figure. Okay, if you consider W is the total weight. Okay, W is the total weight of the area. Okay, it is the total weight of the area. Then for our convenience, we split it into many small regions such as shown in figure. Okay, like small strips with a small areas. Here for an example, this will be the first strip and second strip, third strip, like that. And here the small dots and all shown the center of gravities of the particular areas. For an example, this will be the center of gravity CG1 of that particular area. We know that mass will be concentrated and vertically downward. That means the mass is concentrated at the particular point CG, and then the weight will act exactly downward from the center of gravity. So for this small strip or otherwise the first strip, okay, what we consider in the entire area, if you consider this is the center of gravity, the weight here we are going to consider the W1, that is the weight of the first strip or this small area, that will act at a distance x1 from the reference or axis y1. Okay, here we are going to consider the y as the reference axis. Okay, for x bar calculation. Same way, the second strip, we know that this is the center of gravity to the entire mass of the second area that will be concentrated at the particular point, and the weight W2, okay, the weight W2 that will act at a distance x2 from the reference axis. Same way, this is the center of gravity 3 or center of gravity of the third area. Here the entire mass of the third area will be concentrated at the particular point. So the W3, it means that weight of the area 3 that will act exactly downward from this point, and that will act at a distance x3 from the reference axis. Okay, so if you consider this is the center of gravity of the entire section or entire area, and we know that the W or the total weight that will act exactly downward from this point. Do you understand? And we know that this will be the x bar. Okay, here you can see this is the total weight of the entire area which will be concentrated at the particular point, and then act vertically downward. Here we are going to calculate this distance only. Here, when you are going to use the moment principle, we consider the equilibrium. First of all, what is equilibrium? Okay. Equilibrium force. It is numerically equal to the resultant force, but opposite in direction. Okay. So this W, that is the total weight, that will be the resultant force of these forces. Okay, here we consider only 3 steps. Like that, we can consider many steps in this area, and the distances also, like that we can calculate from the reference axis or YY axis, such as X1, X2, X3, X4. Okay. So the W1, W2, W3, these are all the individual weights of the area, small areas. So the total weight W, that will be the resultant force of the small weights. Okay. So if you consider the equilibrium force, then we have to consider it is acting in opposite direction. Okay. I just mentioned here that is actually the equilibrium force. Okay. It is the equilibrium force. This only we are going to calculate what distance it is going to act from the reference axis. Okay. This only we are going to calculate, that is the X bar. This is the equilibrium force, numerically equal to the weight or total weight of the entire area. Okay. So here, by using the moment principle, we know that the moment made by this W1, that will be W1 and into X1. Okay. When you take moment about the point O, okay, from O, this is the origin. Take moment about origin O. Okay. So first thing is, when you take moment about origin O, this W1 X1, this acts clockwise direction with respect to O. This W1 and X1, that is acting in the clockwise direction. Same W2 into X2, that is also acting in clockwise direction. W3 into X3, that is also acting in clockwise direction. So the moment made by the small weights or weight of the small areas, that will be acting in the clockwise direction, that moments, clockwise moments, or the summation of the clockwise moments made by the small weights that will be compensated by the moment made by the equilibrium force, that is by compensated by W into X bar. Okay, that I am going to mention here. When you take moment about origin, we know that when you consider equilibrium force, then this will be in equilibrium. Okay, so summation of moment about O that equal to 0. Okay, this you can use for any equilibrium objects. Here I'm going to take us clockwise moments equal to counterclockwise moments. Okay, here the clockwise moments that will be W1 into X1 plus W2 into X2 plus W3 into X3, that equal the counterclockwise moment that is made by this total weight and the distance X bar from the reference axis. Okay, so W, that is the total weight, into X bar. So this I can write interchangeably, that is W X bar equal W1 X1 plus W2 X2 plus W3 X3. Okay, then we know that the weight W equal mg or capital Mg, where m is the total mass. Okay, same way W1 that equal to m1g, W2 that equal to m2g, W3 equal m3g. If I substitute all the values here, instead of this W, capital mass or capital M, the total mass, into G into X bar, that equal to M1 G X1 plus W2 that equal to M2G. So M2G X2 plus M3G X3. Here W3 is the M3G. Okay, here you can see left side we can take G as the common. Same way right side also we can take G as the common. Okay, or otherwise I just write one more step, as if I take G, this will be M into X bar. This side if I take G as the common, M1 X1 plus M2 X2 plus M3 X3. So here you can see this side also G is there, this side also G is there commonly, that can be eliminated. So this will be the remaining thing, and further simplifying, so by calculation we are going to get M or the total mass into X bar, that equal to M1 X1 plus M2 X2 plus M3 X3. Okay, Then further continuity of this will be like capital M total mass x bar that equal m1 x1 plus m2 x2 plus m3 x3. So the x bar, if you want to calculate, that equal to m1 x1 plus m2 x2 plus m3 x3 divided by the total mass. And we know that the total mass, m is the total mass of the area, that we can take as capital M equal m1 plus m2 plus m3. So if we substitute the x bar value, we will get m1 x1 plus m2 x2 plus m3 x3 divided by m1 plus m2 plus m3. Okay, so this is the x bar. That means here the x bar is the distance of center of gravity from the reference axis. Okay, center of gravity from the reference axis. Same way we can calculate for y bar also. Okay, y bar means there we have to take x as the reference axis. So for y bar, same way we can take for y bar that equal to m1 y1 plus m2 y2 plus m3 y3 divided by m1 plus m2 plus m3. Here y bar is the distance of center of gravity from reference axis. Okay, and here you can see m1 m2 m3, these are all the values of masses of the individual areas or strips. And we know that density equal mass by volume. Okay, so mass we can write density into volume. Same way we can write m1 equal rho 1 v1, m2 equal rho 2 v2, m3 equal rho 3 v3. If all the densities are same, rho 1 equal rho 2 equal rho 3, then we can write m1 equal rho V1, M2 equal rho V2, M3 equal rho V3. Then if you substitute the values here, okay, instead of M1, we can M1 equal rho V1, M2 equal rho V2, M3 equal rho V3. Instead of this M1, M2, M3 in this y bar equation, then we can write this as y bar equal, instead of M1, we are going to, instead of M1, we are going to substitute rho V1. Okay. So this equation will become rho V1 Y1 plus rho V2 Y2 plus rho V3 Y3 divided by rho V1 plus rho V2 plus rho V3. In the numerator, in all the terms, rho, the density as the common. So we can take y bar equal rho into V1 Y1 plus V2 Y2 plus V3 Y3 divided by the denominator also rho is the common, so we can take out. So we will write V1 plus V2 plus V3. So in numerator also we have the value of rho, and denominator also we have the value of rho. So we can write finally the y bar equal V1 Y1 plus V2 Y2 plus V3 Y3 divided by V1 plus V2 plus V3. Here V is the volume. Same way for x bar, we can write V1 x1 plus V2 x2 plus V3 x3 divided by V1 plus V2 plus V3. When the mass of the objects are given, okay, like in terms of mass, moment of inertia or something, to find out the center of gravity, we will use these formulas, okay, in terms of mass. Then when you neglect the density, or here rho is the density, okay, density of the all the masses are same, all the areas are same, then we neglect the area, we neglect the density, then we will consider only the volume. This will be used in terms of solids, okay, this will be used in terms of solids, okay. And we know that volume, V is the volume, and volume equal area into height or thickness for two-dimension figures or for plane figures. For plane figures, the h equal 1. It means that unity. Okay. This is because for plane figures, the third dimension, which is perpendicular to the plane of the paper, that consider as unity. So instead of volume, we can take area. Okay. So the same formulas we can write as x bar equal a1 x1 plus a2 x2 plus a3 x3 divided by a1 plus a2 plus a3. Same way, y bar equal a1 y1 plus a2 y2 plus a3 y3 divided by a1 plus a2 plus a3. So these formulas can be used when we have to consider the plane figures. That means for the areas. Okay. And the previous formulas can be. So finally, we can conclude it as for masses, when you have to consider the masses, x bar equal m1 x1 plus m2 x2 plus m3 x3 divided by m1 plus m2 plus m3. Same, y bar equal m1 y1 plus m2 y2 plus m3 y3 divided by m1 plus m2 plus m3. Okay, this is for masses. Same for volumes or for solids. Okay, so for solids, we can write x bar equal, instead of the masses, here volume, v1 x1 plus v2 x2 plus v3 x3 divided by v1 plus v2 plus v3. Same way, y bar equal v1 y1 plus v2 y2 plus v3 y3 divided by v1 plus v2 plus v3. Okay. Then finally, for areas or plane figures. Okay, areas or plane figures. For plane figures. Okay, for plane figures, x bar, instead of the volume, here we will consider the area. a1 x1 plus a2 x2 plus a3 x3 divided by a1 plus a2 plus a3. Same way, y bar equal a1 y1 plus a2 y2 plus a3 y3 divided by a1 plus a2 plus a3. Okay. So this is the center of gravity by moment method. First, we consider a small strips and the weights we consider, and from the reference axis or y axis, at what distances the weights will act, that we consider. The total W will be the total weight of the object, but here we consider the equilibrium force, because the total W will be the resultant force. Okay, so we consider the equilibrium force, then we use the moment principle, summation of moment with respect to the O or origin equals 0, we consider these are all the clockwise, and this total weight multiplied with the x bar, the distance between center of gravity of the object from origin. Okay, that moment. Okay, that will be the counterclockwise. Then we use the moment principle. We neglected the gravity. We get the equation for masses. Same way y bar also. For y bar, we have to take x as the reference axis. Then the distances y1, y2, y3 and all, we have to take from the x-axis in vertical dimension. Then for solids, we know that density equal to mass into volume. In all the cases, the densities are same. We neglected the densities on the numerator and also the denominator. Then all the masses as converted into volume. Then finally, for plane figures, instead of the volume, we can take area into the height. The h is the perpendicular dimension from the for the plane of the paper. For the plane figures, if you consider the perpendicular dimension for the plane of the paper is unity, then the h equal 1. Okay, then x bar and y bar we can take in terms of area. Okay. Okay, guys, I hope you all understand. Don't forget to subscribe for more videos. Okay, thank you. Subscribe my YouTube channel, Vishwaguru, a problem solver. Thank you.